bats and gliding raptors. But before I talk about that, I want to acknowledge some of the people I've worked with. At Brown, I worked with Sharon Swartz and Kenny Breuer, and it was through their collaboration that I did all of the bat research that I'm going to present at the end. And then the majority of the talk will probably focus on bird flight, and that was in collaboration with the Royal Veterinary College as well as the University of Bristol. And I'd like to especially point out Jialei Song, who's currently at the Dongguan University of Technology in Guangdong, China. He was really the CFD guru of the group, and so I'm going to present a little bit of the CFD work that we did to investigate morphing in bird tails. And of course, the reason we're looking at animals is that their capacity to fly is really unrivaled, and it's quite remarkable. So here's a bat who's doing a turning maneuver. And what you're going to see on the next wing beat right here is a large span-wise camber, and you're also able to see how thin the wing membrane is. It's really quite a remarkable structure. Then over here, you're going to see it undergo a large aeroelastic interaction where it sort of flutters and vibrates as it flaps, where you can see how the lift influences the shape of the wing membrane. And it's these kind of questions that kind of interest me. How are wings morphing? And really trying to get at the details. Similarly, we can look at things like eagles flying. And while the other one was a normal flight maneuver, this eagle's about to get hit by a giant upgust equal to about its flight speed. And it just flies straight through it through some morphing mechanism by which its wings are pitching. You can tell the wings are pitching down a little bit, and the wings are elevating, which is likely stabilizing the body. And so there's quite a bit of beauty and amazing features that we can pick up by looking at natural organisms and how they fly. So today's talk is really broken into 4 sections. And at the core of it is really just measuring wing shape, using photogrammetry, using videogrammetry, effectively to understand all the little details of a wing and a tail and a body, and understand how they change shape during a maneuver or during a speed change or things like that. The second section is really about all of the patterns that we see in the 3 birds flying. And one of the things that kind of comes out of this is that the wings themselves change quite subtly. It looks quite grossly large, but when you kind of align everything up, you see that the wings are making very small adjustments. It's really the body and the tail that make quite large, dramatic changes. And that might have some important implications for how we think about where we put our actuators in a flyer. The third section is going to get into some CFD, so utilizing these wing shapes and how we might understand tail posture better and why the posture of the tail is important. And the last section is really about bat wings, really about membrane wings and muscles that likely control camber, not through explicitly controlling shape, but by modulating the tension on the skin. And so let me start with this little introduction bit. It's quite brief. So the way we do measure wing shape is using photogrammetry, which is basically disparity maps or feature recognition. What we do is we have arrays of cameras looking above a bird and below a bird, and we have it fly down a corridor into this space in between the cameras so we can see the undersurface and upper surface. And this is pretty accurate because we can compare what we'd get from these calibrated cameras to that of a really precise laser scan, about 50 micron accuracy. And if we take a laser scanned model of a bird, so this is not a real bird, this is just a fiberglass model, and we color code it based on the error, what we see is in general, we're sitting well below 1 millimeter in error. Everything yellow is less than 1 millimeter, everything orange is less than 2 millimeters, and so forth. So you can get really high accuracy using these techniques, as long as you're very careful about calibrating your cameras. And we can do this with an actual bird by taking images such as these. So here I'm showing you the 3 upper pairs of cameras, color-coded red and blue for the left and right pair, and the 3 lower pairs of cameras, color-coded red and blue. And so together you can kind of take all of that data and you can basically build a beautiful 3D detailed beautiful point cloud of the bird. And through a lot of work, way more work than I expected, you can eventually build 3D geometries that are useful for things like CFD. But importantly, you need to do this for thick wings. Here, a bird's wing is about 10 to 13% of the chord at its peak thickness. When you're dealing with membrane wings, you don't have to do that. So a bat here, a bat's wing membrane thickness is well under 1% of the chord. So to give you a sense of the actual thickness, they're probably about 50 microns thick, depending on the species. It's incredibly thin. And really there you can just set up cameras above the animal and you can reconstruct the shape of the wing just on the upper surface. And you know that the lower surface is basically the exact same, given how thin the membrane is. And so that's kind of going to be the foundation of the talk. So everything's really about measuring wing shape and trying to understand what it means. So this next section is really about patterns, and I'm going to be open here. We don't understand a lot of wing shape in birds. I think what we've managed to do here is identify a lot of interesting questions. But one of the take-homes is that the changes that happen in wings are quite subtle. So if we can understand these gross patterns, we can begin to understand the morphing quite well. So for this, we looked at 3 different birds: a barn owl, a tawny owl, and a goshawk. And I'm always going to present the data in this order, top to bottom, and also with this color coding: blue, green, and orange. And we flew these 3 birds through a photogrammetry setup 13 to 15 times each. And because they were able to fly at their own speeds, and they were always gliding, I should say, they adopted various gliding speeds ranging from about 5-ish to about 9-ish, depending on the species. And what we would do is we would take the 3D models that we'd produce from photogrammetry and we'd segment them up. So we'd have the tail segment, we'd have the both wings segmented, and then we'd have sort of the head and torso segmented as a unit. And what everything I present will always have the 2 wings lumped together. So the left and right wing we're treating as if they're the same shape, and we're going to take averages based around that, which should seem like a kind of risky thing, because if you ever measured your feet, you'll be aware that your left and right foot are not the same. But one of the things that I think is surprising here is that left and right wing actually do look almost identical. And once you segment out these elements, you can actually begin to align the animal's configuration based around those segments. So here, what I've done is I've aligned all of the planforms based around the torso and head. And you can start to see how the wings and tail vary slightly from sort of these dorsiventral, these top-down projections. And you can see there's very little planform variation in the barn owl, a bit more in the tawny owl, and quite a bit in the goshawk. But what I'll point out is as soon as you try and align the wings, a lot of that variation actually goes away. So here is all the barn owl wings aligned, tawny owl, and goshawk. And there's not a lot of variation, even though we're seeing quite a bit of change in how the wing is held. The actual shape is quite subtly changing. And further that point, I can show you some data about sectional pitch. So this is taking chord sections and looking at how vertically oriented or inclined they are. So as a function of the span, or I should say the semi-span. So this is from the shoulder or the root to the wingtip. And one of the patterns that comes out of this is that as you move along from the shoulder out distally to the wingtip, the wing starts to pitch up in all 3 species. And similarly, if you do the same thing for peak camber, so the maximum camber value, you get the opposite of pattern. So the camber starts to decrease as you move from proximal to distal. And not surprisingly, we can basically take this plot and plot it against itself, and we see that there's quite a nice inverse relationship here. This plot can be a little bit confusing, but basically the squares are the shoulder, the root, so here, and the triangles are the tip. And every time you see a circle, that represents about 10% of the span position. So you can see the only time we really deviate from this path is about the last 10% of the wingtip in the goshawk, Accipiter gentilis, which is just kind of right here. But otherwise, we get a pretty nice inverse relationship. I have no clue why we have an inverse relationship. If anyone has thoughts, I'd love to hear it. But I think this is kind of one of the interesting findings we come up with, and it happens in all 3 species. And so that's why I wanted to share it, was because I thought it was quite interesting. Oh, and importantly, one of the things I wanted to tell you is that if you look at these plots, the dashed lines are the means that we reported. If you've got enough resolution, you can see that there are some very fine shaded areas. Those shaded areas are the standard error. So that standard error, a lot of the time, is actually thinner than the average line. And that just kind of gives you a sense of how well aligned these wings are, basically how subtle any changes are in things like chord pitch and peak camber across all the flights. These wings are actually holding very much the same overall configuration and really not changing a lot, despite flying at different speeds. They change a little, but not a lot. And I can show that again with parameters like wing thickness. So here is a projection of the wing thickness for all three birds. I've just remapped it onto a rectangle here. So top to bottom is the percent chord, and left to right is percent span. So these should look almost identical, but all we've done is just converted a more elliptical wing into a rectangular wing. And then on the right is our standard error, basically a measure of our variation. And you can see that wing thickness is almost always the same, meaning the wings, not surprisingly, are not changing that much, and our error isn't very high. We can also do the same for camber, and this is where things get kind of fun and interesting. If we plot wing camber across the wings, so this is no longer peak camber, but just sort of the camber profile. Excuse me. We get some just interesting distributions. If you look closely, you'll see in general there's sort of two peaks of camber in all of these birds. Don't know why, but these are the kinds of questions that we can start to address now that we understand nature's doing it. Is it a good idea, or is it a feature of how a bird is built? Basically, part of my goal in presenting this kind of work is to get more people thinking about the kind of data we can produce using photogrammetry. And so what I just showed you was how similar the wings are, and they really don't change a lot, even across all the flight speeds, but they do change. So if you take the measurements and plot them against speed, you do see small changes. So here I calculated the peak camber across 3 wing sections, just breaking the wing up into fourths and taking the intermediate point, and I plotted peak camber as a function of flight speed of each of those. And in every one of those, peak camber is decreasing. So the wing is effectively flattening out as it flies faster. And you can do the same thing, except replacing peak camber with just overall camber profile. And you can plot that as a function of flight speed. And you can see yellow means it's decreasing, blue means the camber is increasing. And you can see really throughout every bird, camber has a tendency to generally decrease as a function of flight speed. So this is kind of one of the rules we can pick up, is that as a wing wants to fly faster, it wants to flatten out in order, if we're to try and sort of mimic what birds did. This makes sense because when we look at other morphing wings, we typically find a good rule of thumb is reduce camber as you fly faster, increase camber as you fly slower. So, hey, that's always kind of nice when nature does what it should do. And the last parameter I wanted to talk about was angle of attack. So here, if we look at the angle of attack of wing, this is basically the rotation of the shoulder along the axis. We can see that the wing as a whole tends to decrease its angle of attack as the birds fly faster in all 3 species. And we see the tail tends to, if you think of the tail as a separate wing, which is a whole topic of itself, also tends to sort of flatten out, so reducing its angle of attack relative to the airflow as you increase in speed. These things kind of make sense. We typically would predict this based on morphing studies, but it's nice to see birds doing what we think they should do, because it means we're kind of on the same path, same trajectory. And what I want to leave this section with was kind of a point that I think is quite interesting. If you look at all of the chord profiles in one section of a bird wing, here I've separated them out by bird, barn owl, tawny owl, goshawk. I've color coded the slowest wing in blue, so it's kind of hard to see, but it's there, and the fastest flight profile in red. And what you can hopefully just barely make out is there's a small difference where the red outline is a little bit flatter than the blue outline. It's really subtle, right? The wings don't morph a lot over this speed range. They do morph, they morph consistently, but it's a very subtle thing. If you do the same thing for the body profile, the body and wing profile, which is actually a wing as a whole unit, you see it's this section that's really undergoing dramatic morphing. This goshawk shows a hugely different camber profile and overall different configuration, whereas its wing is subtle. And all this is to ultimately lead to, if these kinds of questions interest you, we have geometries available. So we definitely would love to see more people working on this stuff. So here is a geometry from Tyto alba, as well as the goshawk, Accipiter gentilis, and they're available in our published papers. These are from actual flights, so all of the awkwardness is there. So this goshawk did have its right wing slightly tilted downwards. It's not symmetrical, but it is basically trim. There's no there's very low accelerations in rotation or lateral accelerations. So these are out there if anyone wants them to add analysis to. Okay, so that was the plea to get more people to do more work on morphing and bird wings. Now I'll tell you how we used our geometries to understand the tail. And so what I've told you already is that the tail really is quite a dramatic morphing relative to, say the wing. And so what we did was we took this same geometry and we caused it to pitch up and down, as well as spread and contract. And what we were able to then do was simulate the CFD. In this case, we simulated with ANSYS and using the turbulence model K omega SST. I should say what I mean is Jale did this, and Jale conveniently came onto the talk just for any questions, because I know many of you are quite interested in CFD. So really, I'm reporting Jale's part right here. But we had the fundamental question of, is the K omega SST model sufficiently accurate to understand tail morphing? And so what we did to address this is try and validate it. We validated it by comparing the results from CFD to measured wakes. So the video I'm about to show you are birds flying through a mist of soap bubbles. These soap bubbles are about 300 microns in diameter. They're filled with just enough helium so that they're neutrally buoyant. They don't rise, they don't fall. They effectively stay in the same spot until an airflow like that produced by a wing causes them to move. So here's some videos of the goshawk and tawny owl. And so you get some very nice, you can resolve some very nice wingtip vortices. You can also pick out that there's quite a strong downwash behind the tail. And they make very, very pretty videos. So I always figure out a way to include this into every talk. So these aren't just pretty though. You can actually track these soap bubbles. And so if you use a particle tracking velocimetry method, which LaVision produced, but there's, I believe, some open source ones now available as well. You can track these soap bubbles and color code them by speed or whatever. In this case, we've color coded it by vertical velocity, where blue is down, red is up. And you can really begin to sort of reconstruct the 3D wake produced by a gliding bird. And when we do that, we get wakes looking like this based on Q criterion, or we can do something like compare the downwash. So if we look at the downwash from 3 different flights, this is yellow, pink, and aqua, against the CFD model. Now realize the bird does not have the exact same geometry as the CFD model, but a similar one. We get generally pretty decent agreement, particularly on this left wing. So that gave us some confidence that the K omega SST model is actually producing a pretty good downwash representative of what the bird would be producing. We get about 94% of body weight support. And then we can look at things at drag using more elaborate CFD models. So in this case, we use large eddy simulation, and in general, large eddy simulation produce a very similar drag value, except at like 46 degrees tail pitch, where in that instant we were about 5% off. But in general, it agreed quite well with the K omega SST model. So, and it produced 2% more lift. Nuance. So all of that's to say, we used the K omega SST model in part because it gave us pretty good results comparable to what we were measuring in real life. And it was very, very fast. So we could do a lot of different geometries. And so we kind of looked around at the different configurations birds could adopt. And when we estimated the lift and drag produced by an array of tail pitches and an array of tail spreads, we saw what is fairly predictable. As your tail spreads out, you generally get more lift and you get more drag. As your tail increases in pitch, you get more lift, you get more drag. That shouldn't surprise anyone. This is with the bird's geometry at a sort of fixed angle of attack. However, what's important to realize is that this is deviating from weight support. So what we can do is we can rotate, we can pitch that geometry in effect and try and change the angle of attack to get it such that we only have weight support. So we can get rid of this plot and just ask, what is the drag when weight is actually supported? And when you do that, what you get is this plot, quite different from the original. You see that there's now a minimum in a region around 20 to 30 degrees tail pitch. And that when you deviate away from that, you start to increase your drag quite a bit. And these little black dots, and as well as this asterisk, are the flight geometries that we observed in the barn owl flying at the same speed as our CFD model. So what we found were that the barn owls tend to fly at the speed and with the tail configurations that were kind of within this minimum well, basically meaning that their tails tend to adopt a configuration that reduced their drag, that kept them at their minimum drag. And I showed you that tail area and tail pitch should change as a function of speed. And so we can repeat what I just showed you, which was done at one speed, but do it at an array of speeds. And in this case, we can do it at 6.5, 7.5, 8.5, and 9 meters per second. And what we see is that tail pitch will tend to decrease as you increase in speed. If you can see the minimum, which are quite hard to see, and I apologize for that. That's on me. And then tail spread tends to go from wanting to have maximum spread to minimum spread as you go from slow to fast. So the actions that we predict based on CFD are broadly consistent with what we actually record in flying birds. And so that's kind of just a nice way of learning about what the tail is doing. We probably could have predicted that it was doing it, but now we can quantitatively say that it actually does so. Now, this last section is really about bats. And what I want to talk to you about is our membrane wings and how they're controlled. So, some history, some background. Bats have these really weird muscles inside their wing membrane. Here's its head, here's its tail, here's its left wing, we'll say. And these muscles don't touch any bone. They insert on one part of the membrane and then in the other part of the membrane, and they cross no skeletal joints. What they seem to be doing is basically tensioning the tissue. So if you were to take a cross section through the wing, it might look something like this. You have this membrane in white and then a red area, which is the muscle. And the thought with membrane wings is that the aerodynamic force kind of pushes upwards on the wing, causing it to billow, causing it to camber. And that these muscles, if they activate and tense and contract, they will flatten and cause camber reduction. That's been the hypothesis. The only thing we know about these muscles is that they tend to be on during downstroke, which is kind of what you'd expect. So if you were to try and read their electrical activity during downstroke and upstroke, here I'm plotting a rose plot. This is downstroke, this is upstroke, and I'm plotting the percentage of time we could measure electrical activity in the muscle. It's a very noisy measurement, so it's not super clean. We see overwhelmingly activity during downstroke and very little activity during upstroke. And so that's what we know. These muscles look like they could be camber controllers. They seem to be active during downstroke, but what their function is unclear. So what we wanted to do with photogrammetry was measure the camber and turn off the muscles. So in this case, what we did was we injected each of these muscles with botulinum toxin. So Botox is what it's commonly referred to. So this causes a temporary paralysis that lasts for weeks, but not months or years. And the bats thankfully do recover. And so we could turn off the muscles and then fly them. In this case, again, we flew them in the wind tunnel. We set up cameras above them, and we could measure the shape of the wing. And in this case, we're only going to ever think about two areas of the wing, two chord profiles. One is in the hand wing, where there's no muscle, and the other is right here, where there's the most longest muscles in the arm wing. And we can compare those two to see what changes when we turn off these muscles. And so the two parameters I'm going to present, I've already talked about, but I'll just repeat myself, is things like angle of attack, so the angle of the airflow relative to the chord of the wing. This here is a chord profile of the arm wing. And we're also going to talk about camber, or peak camber, which is the red dashed line. So basically the maximum distance from the chord line, normalized by chord length. So here is a chord profile of the arm wing, and here is a chord profile of the hand wing. Now, for the experiment, we measured only at mid downstroke, and that was just to simplify our life. At the time, this was actually the first time we were doing photogrammetry, and it was quite elaborate to kind of get everything working. And the perturbation was quite difficult to actually do. It was quite a few injections and quite a challenging surgery. We studied 3 different bats, get measured at mid downstroke, and we had a couple hypotheses. Look at us, like real scientists, you know. We kind of knew that in normal flight, any animal should generally have less camber at faster speed. So we kind of expected that muscle paralysis should be greater at the faster speed. I'll tell you now, we can't actually address that in this study, but I'll get to that. But for that reason, we want to test the bats at 2 different flight speeds, once at a slow flight speed and once at a fast flight speed. The other hypothesis we had was that if camber is going to increase, then lift and drag will also have to increase. And so therefore, the bat will have to compensate kinematically in some way for this increased lift and drag, maybe by reducing its angle of attack, or maybe by flying slower, who knows. And so the parameters we measured were amplitude, angle of attack, and downstroke angle. And now this is kind of a busy plot, so I'll kind of build it up slowly. So we measured maximum chordwise camber, which I've plotted here for the arm wing, here for the hand wing. Again, arm wing has muscle, hand wing has no muscle. And we're plotting it against inverse dynamic pressure. Now, that might seem a little odd, but I'll explain. In effect, if we kind of create a term, vertical force coefficient, and we talk about dynamic pressure, which is 1/2 rho v squared, we can say that weight support should be Q CV S. So surface area, vertical force coefficient, and dynamic pressure. And I'll tell you that wing area doesn't actually change very much, only about 2% across these flight speeds. So in that case, what we could basically find is that the vertical force coefficient is approximately proportional to inverse dynamic pressure. And so that's why we decided to plot against inverse dynamic pressure, because we thought camber would probably scale approximately to this sort of force coefficients. And so in this case, as you go from left to right, you have flight speed decreasing left to right, but vertical force coefficient increasing. And so I'm only plotting the control data here, just to warm things up. And so you can see camber does in fact increase as you go to higher force coefficients. And when we plot the Botox data, we see in the arm wing, the wing is in fact cambered substantially more. I think it was about 10 to 15% greater on average, whereas the hand wing shows no difference. Now, the astute of you will notice that there is no Botox data at the low flight speed. And this was really surprising to us, but the bats actually couldn't sustain flight at the low flight speed. So what we had done was we flew the bats in the wind tunnel with the wind tunnel off and with the wind tunnel at 5 meters per second. And as soon as we turned the wind tunnel off, they fell and crashed immediately. They couldn't sustain flight. They immediately descended to the ground. This could be because of increased camber. This could be for many reasons. So ultimately, I'm going to say don't read too much into it. We don't know why they couldn't sustain flight at low flight speed, but that was kind of an interesting result. So we only have data for the Botox flights when they're flying in the wind tunnel at 5 meters per second tunnel speed. They're of course flying slightly faster than that. And if we compare the control flights against the Botox flights, we do see that they end up flying overall slower. So they end up being in the wind tunnel longer because they travel slower. So the kinematics that they end up adopting to compensate for this increased camber are that we see an overall larger wing stroke, and the wing stroke ends up being more vertical. So if we plot amplitude of the wing beat, we see that they end up taking a substantially larger amplitude. Basically, they end up increasing their wing beat amplitude by about 20 to 30 degrees. And they also end up, not surprisingly, flapping more vertically, which should help sort of tilt their aerodynamic force vector more forward to help basically counteract the increased drag that they're probably experiencing from the increased camber. We see no change in angle of attack relative to sort of our linearized model in either the arm wing or the hand wing. So that's really it. So basically what we have found is that these muscles do seem to increase camber or decrease camber when they're active. But beyond that, they also probably play a very important role in the actual shape that's being adopted. What I've plotted here are all of the camber profiles that we measured in the slow control flights, in the fast control flights, and the Botox flights. And down here is just sort of a summary average. And one of the things you can see is that the red Botox profiles, they follow the slow flight wing shape at the leading edge and the fast flight profile at the trailing edge. So really, when we turn off these muscles, we're not just changing camber, but we're actually quite dramatically changing the profile that's being adopted. What that means, we don't know. But I think there are a lot of interesting and open questions that arise from actually being able to kind of pick up the detail that this photogrammetry method gets you. And so, yeah, that's really all I have. I just want to conclude with a few thoughts. So I've shown you photogrammetry in birds as well as bats. One of the great things of working on membrane wings is that you need about half the number of cameras because you can just record from either below or above the animal. You basically know the wing shape because of how thin the membranes are. And I've shown you that there are quite a few weird, counterintuitive ways to build wings that birds adopt. And they're fairly repeatable, things like these sort of bimodal distributions of camber, peak camber. But that these are quite repeatable, and we can begin to sort of assess why they're doing this through using sort of CFD, taking these geometries which are published, openly available, and warping them so that we can ask questions about the geometries, things like the tail's pitch or the tail's spread, and trying to identify the many reasons why animals are built the way they are. Some will be for drag, some will be for stability, some will be just because evolution's weird, but it's nice to try and parse these out. And I concluded by telling you how we can also use this technique in conjunction with other techniques to begin to look at wing morphing muscles. So in this case, I showed you how we can parallelize muscles in a bat's wing and how that's going to lead to different camber profiles, which tells us that these muscles are in fact camber modifiers. And really there's not much else in nature like them, which is quite interesting. So it's quite cool to see a muscle that is clearly not a shape controller because it doesn't attach anything stiff. It's some sort of force controller. So it's not positional, but more of a force controller, kind of more in line with sort of how we think of soft robotics nowadays. And then I'll end with a plea to please download these models and do more CFD, because I really want to include this section, even though it's clearly a very loose section of the talk, because I know a lot of you do think about CFD and could offer a number of insights. And I just think sometimes it's getting the material into the right hands. Yeah, thank you very much.
Yeah, thanks for this amazing talk. So this is very impressive. If anyone has any questions, you can just open your mic and ask questions, or you can leave your question in the chat.
Yeah, and I should say, if you have a burning CFD question and you don't think I can answer it, I have recruited Jolly just for that purpose. So he is here.
Hi, Jorn, I'm here. Yes, but I have to apologize that at the beginning, so I missed the beginning of the talk because something went wrong on the platform. So it took some time to fix that.
Okay.
Now I have one question. So, you give a very brilliant talk and talk about the bird and the bats. So for both bird and bats, so the camber changes with the speed, right? So I guess the variation of the camber, so depends on several factors. Maybe yes. due to the aerodynamics or maybe the active control, right?
Yeah, no, yeah. I think there's a lot of covariance. Yeah. So I think what you're trying to say is, what is the rule? Like how much should you change your camber with speed, right? We see we see that pattern in engineered wings. We see that in birds. We see it in bats. But how much? Is that right?
No, not how much. So I'm wondering which factor dominates this. So it's due to the aerodynamic force or due to the active control?
Okay. So for so for bats, it's almost certainly due to active control, and that's either those muscles I showed you or actually the skeletal elements. Because what will tend to happen with a membrane wing is, as you increase force on it, it will tend to billow out and camber and increase more. So we would generally predict, with no active control, a membrane wing to increase camber as a function of flight, increased lift, I'll say.
Okay.
But yeah, sorry. So I guess but if weight is maintained, which it is in all three configurations, I guess the answer is I take it back. I don't know. I think it's a very good question because of course, weight support is basically constant across all of these flight speeds. So why are they changing? I assume it has to be active control and not a passive thing, because there isn't much, because otherwise it would have to be basically shear force that was causing the wings to change camber. And I just don't think that's likely the case, since they're under basically constant lift, constant vertical force. Would you agree with that? Does that make sense?
Yeah, I agree with that. But yeah, maybe later we can use safety to check that, to check whether it's passive or not.
Absolutely.
Thank you.
So any other questions?
Hello.
Hi.
I have a question. It's a very impressive talk. My first question is about the pictures you shown on the left. How, maybe I missed it. How can you generate the bubble floating in the air?
No, sure. Yeah, no, I didn't really go into that, mostly because we can spend a long time on that, and it was something we did a few years back. So we worked with LaVision, who is a sort of fluid, they do fluids, really computer vision company, I think, at this point, but a lot of their work has been on developing technologies to measure fluids and mechanical deformation. And so in this case, they actually produce both a jet that will produce these soap bubbles, as well as code to track the soap bubbles. There are open source versions for these jets you can find published. So you'd be looking for PTV, particle tracking velocimetry, to find open source versions of this, because I think LaVision's kit is really, really expensive. And we basically got it on loan because they just wanted someone to demo it and tell them what was, help debug it. So we got to be the guinea pigs to both produce really pretty videos and also tell them this bit of software doesn't work, this bit of software doesn't work, this bit of hardware doesn't work. But yeah, does that help?
Yeah, thank you. But I mean, what kind is helium? Is soap bubble?
Yeah, it's I believe they're using, they have their own proprietary soap formulation, which they'll charge you for. But yeah, basically you can use soap. I think you end up wanting to add glycerin to make it extra durable, and then a mixture of helium and air, and it's getting that helium air mix just right to get it neutrally buoyant, which I think is part of their part of what they sell as being their engineering. But I promise. Yeah, it's been a while since I looked up the open source stuff, yeah, there is some material on that, including like 3D printed nozzles and things like that.
Okay. Thank you.
Yeah.
Thank you. Yeah.
So one person asking how you catch the bats. So I'm pretty sure it's always a warfare of animals, right?
Yeah, no. So we had a colony of bats at Brown. So the bats were all used to being handled. All of these bats knew me quite well. I know that's a silly thing to say in some ways, but I'd worked with them for quite a few years prior to this, and we'd done. So they were quite used to being handled, generally pretty well behaved. We had to anesthetize the animals, so the animals were under isoflurane to minimize any sort of impact on their behavior, and to kind of minimize the trauma. But we did end up basically injecting the bats with about, what was it? I think 30 microliters of liquid per muscle. So it was basically a pinprick. Importantly, I should tell you that the wing membrane, its thickness is about 50 microns, but we're mostly piercing just the outer layer. So we're only basically cutting through about 30 microns of skin to reach the muscle. So it's a very, very tiny slice, about 150 microns wide, if I recall, and then just very gently injecting, putting the needle next to the muscle and injecting the fluid with a micro injector. When the bats awoke, they generally seemed okay. They didn't seem to notice the effect of the injection, but every once in a while one would scratch at it. So I think there's some effect of it, an irritation of it. And we always waited a week before we actually flew them and did any measurements. Does that cover sorry, was this in the chat? I can see.
Yeah, thanks, Dr. Cheney. So actually, I have one question. When you mentioned the best posture for the tailwind, I'm wondering, like you mentioned, like how you host the weight of the eagles. But essentially, the lift, I think, is coming from the wing itself, not the tailwind. So why you mentioned the tailwind has to help to suspend the birds?
Oh, I guess that comes from some other work we've done. This is something that Jolly had spent a lot of time on. But if you were to take what you find is the airflow around the body and wing, the body and tail, I should say, is quite dramatic and actually has a large impact on the sort of aerodynamics of the bird's wing. Jolly, do you recall what do you recall any metrics? But what I can tell you is basically if you get rid of the tail, you lose quite a bit of aerodynamic force production. So the tail is actually doing quite a bit, even if the actual pressure differential on it is rather small.
Without a tail, the lift drop is small, not very large, I think.
So what's your mission, Charlie?
I mean, without a tail, so I mean the force generated on the tail is not very large. If you just look at the integrated model, so if you just look at the lift on the tail, it's not very large. But this lift can influence the flow around on the wing, on the body surface. So in that way, it will influence affect the overall aerodynamics of the whole bird.
Okay. Now I understand.
Okay.
Well, thanks.
Yeah.
Yes,
Well,
thanks.
and I'd also point out some work back to, I think maybe 2 decades ago at this point. Some birds will flap their wings and then just bound, so they'll hide their wings and just basically bullet through the air. And people have done PIV around those bird bodies, and they're actually producing a decent amount of lift. So the whole body plan form is actually quite an effective wing, despite it looking a little bit chubby, I would say. It's a very thick wing, but it actually still produces effective lift.
Yeah, smart
sense?
birds are different, I guess. So the person is asking, is there a tailwind in bats as well? Like, I guess it's asking how the bats like actively balance his flight.
There is, but it depends a lot on the species. So in all bats, they have, let's see if I can make out enough detail here. So in all bats, they have some bit of membrane. So here's its right foot, here's its left foot, there's its head, there's its leg. There's a small membrane right here and a small membrane right there. And this bat has a very short tail. But some bats have a longer tail, and when they have generally a longer tail, most of the time they'll have a much larger wing membrane. Not always true, but in general. So yes, bats do have a tail membrane, but it depends a bit on the species you're looking at. The species I looked at, it doesn't have much of any sort of membrane, but a little bit. And that tail membrane also has muscles in it, which is kind of cool. So it's not just the arm wing that has muscle.
Essentially, you think like these little membrane is also could balance maybe the moment like when they do like maneuver.
Yes, I think certainly it'll have an impact on that. The other really important impact is it's a great thing to catch insects with. So this bat that I'm showing you is mostly frugivorous, and mostly it's fruit. A lot of the bats that do have a tail membrane, the bat will actually fly, flap, 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 flap. There's an insect here. Many of them will actually curl their abdomen, catch the insect in basically the tail membrane, and flip it into its mouth and then eat it. So the other important bit of it is pure predator catching or prey catching. So yeah, some of it will definitely impact moments and torques, but some of it's just going to be for the other functions of life.
So another person asks, how will the feather textures affect the bird aerodynamics? Will CFD be able to answer this question?
Yeah, I think at the really fine level of texture, I don't think we can pick it up. So we can, I think with enough measurements and enough detail, we could pick out the sort of the really subtle features of a bird wing. But overall, we do have to get it into a usable CFD model. There's quite a bit of smoothing that has to happen. So that sort of micro texture effects, which are very real, they do get washed out in our CFD models. So I think if you want to look at that, you would probably start with a smoothed out model and then apply sort of that micro texture so you could get at that kind of subject matter. But I don't think you could measure it and trust it with our current imaging technology, or without being a lot better at this than I am. And I'm pretty good, but that help? Yeah. So it's a it's definitely a thing we have to kind of ignore at this stage, but is worth pursuing.
I guess it's very challenging as well. So essentially, I have one more question for you. Like many of this research, you look at the bird flight from sort of the changing of the interfaces. But essentially, you showed you have CFD tools. You have the Shakes box, I suppose, like you just showed the PTV, which is like why you don't just use helium bubble and like measure the flight in helium bubble and then reconstruct the like sort of aerodynamics and then see how they go there and for one cycle the lift and drag there. Why you look at interfaces?
Well, so part of it is that, I mean, getting drag is still a nightmare it's a nightmare measuring it or simulating it. So I think regardless, drag is always going to be quite difficult. But the main reason to do CFD in my mind is that you can only measure what an animal does. You can't measure what it doesn't do. And so what we, when we measured those tail configurations, we could have perhaps estimated the drag, but we wouldn't have known really that the drag was increasing outside of it. We could have seen that, yes, the birds all produce about a similar drag despite the same tail pitch and spread, but we wouldn't have had the rest of this heat map. So we wouldn't have known that it happened to be near the minimum drag. So I think the really great thing about doing CFD is asking the questions about, yes, the animal does this, but why doesn't it operate here or there or there? And we can't force an animal to do this, just for oftentimes for welfare reasons.
Yeah, that makes sense. So is there any other questions? We'll take the last question. So the person asking, I was wondering what you might study next. Will you stick with bats or perhaps look at other gliding mammals?
Yeah, so I think
gliders or flying squirrels, for example.
Yeah, so actually flying squirrels and sugar gliders are probably where I'm going to focus my energy next, because it's a nice hybrid of the two, going from gliding birds to membrane wings and bats. The questions I'm interested in and thinking about are how membrane vibrations might impact evolution of flight, because there are certain domains in an angle of attack where a wing will start to vibrate, and then the lift that it produces, the drag and the pitch, become incredibly unsteady, and it might be quite hard to fly in that domain. So yes, actually, most of my current grants I'm putting in for in the coming months all have to do with gliding squirrels and sugar gliders and the like. So yeah, that's kind of where I want to put my energy into, because I think it's a nice unexplored area.
Yeah, thanks for everyone for participating in the IBiM talk. And thanks Dr. Jorn Cheney to give this impressive talk here. So we'll see you all in next week's IBiM talk. Thank you for participating. Bye.
Thank you, everyone.